Okay, this is now our final lecture on models, activities to model, and modeling in computer science, other sciences, and engineering. We would like to finish now this series of lectures with an epilogue, discussing what could be done in future, what should be done in future, and what are the most important benefits of modeling. We have had a good number of lectures so far. Now with the epilogue I would like to complete these lectures. Let me start with a statement that comes up there quite often. George Edward Pelham Box is often cited with all models are wrong, but some of them are useful. Obtain a correct one, alert to what is importantly wrong. It is often claimed that modeling is not necessary, like Peter Norvig from Google made a claim, maybe it is true, that all models are wrong and increasingly you can succeed without them. I think we should somehow try to discuss it by a number of observations. First of all, I would like to go for a number of arguments against modeling, myths that we can observe, and we should have an answer for the question why we need a foundation of modeling. What can be done, what should be done, what have to be done to overcome the current state of practice in computer science, in which models are heavily used, but not the primary matter of teaching and investigation. In 2008, we have had a pretty nice talk given by Wolfgang Kesse, and he summarized his observations on modeling. But they do not know what they do. We have a Babylonian confusion and muddle. It is not a bug, it is a feature. De facto standards and lobbyists are claiming completely different things than MMM, models, activities to models, and the modeling and modeling. Why I should cope with that, what was the state of yesterday. Each day a new wheel, new buzzword, without any sense, a new trend, a new hype, and we forget about what we have been learning in the past, without consideration of the value of the model that is really observable everywhere. Locum forever. We have maybe no sound mathematical foundations yet. Take but don't think. Take it only without critics. The model. Academia is working in ivory tower and people in practice are completely differently working. And I think we should overcome this situation. Let me continue this line of observations with a number of myths that go back to Scott Embler. We rephrase them a little bit. First of all, modeling equals documentation. That is not really true. Modeling is not really documentation. Maybe these are orthogonal matters, and for this reason we should maybe consider modeling in a completely different way than only for documentation. Also, the first modeling approaches have been mainly oriented on documentation, at least in the area of database modeling. Modeling is far older than computer science. It is at least 3,000 years old, and for this reason we should maybe not consider this part so very seriously. Often we claim that we can start only from scratch. That is not really true. Models exist, models of models and models of models of models are developed, and furthermore we are looking for having a good way somehow to use a model for generating a program. This was chapter 14 in this course. Another claim is modeling implies a heavyweight software process. That is not really true, because if we first maybe are developing some kind of mental models for our perception, And then we develop something like a proper model that we can use for software development. That means we have at least a model suite. You must freeze requirements and then you can model, is an often made claim. That is not really true, because we have models or model development as a brownfield methodology and not only as a greenfield methodology. We should have models that allow us somehow tolerate evolution. Maybe we should have some kind of componentization. Maybe we should have high quality resilient inner models and outer models as changeable components that can be replaced whenever it is necessary. Your design is carved in stone is often claimed. Again, that is not true, because we need to have some kind of evolution tolerance. And we should be aware of evolution in applications, in our infrastructures, in our thoughts, so that we have maybe some kind of evolution awareness. We claim often you must use a case tool because models might become very complex. That is not really true, because a case tool is also a little bit dangerous thing, since in a case tool we have already incorporated a number of assumptions. We have a grounding in some kind of deep model that we must learn first, and then we must know what we can do with this case tool. Often it is claimed modeling is a waste of time. Okay, start from scratch like we do it in extreme programming, in agile programming, but in this case still you have a model in mind, and then you develop the model over implementing something. Database people and some other people think that the world revolves around data modeling. That's not really true. Models include a lot of different aspects and facets. So in this case, of course, we must have a model suite, and then in this case, one of the models in the model suite might be a data model or a database model. It is also claimed that all developers know how to model. That's also not really true. We have modeling, since it is a very engineering activity, then in this case we should know how to do properly modeling. People also think that modeling is often independent on the language that we use. We claimed already in chapter 4 that this is not the case. Think about Sapir and Worf. Languages, of course, enable, but they are also restricting our expressive facilities. And languages bring a lot of biases. So in this case, we should be somehow able to change a language whenever it is not convenient. And we should not only work with formal languages, we can also work with natural languages, and we can also work with some kind of web of notions, web of concepts, web of terms. And in this case, a language, at least a formal language, is not sufficiently expressive. There are other myths of conceptual computer science modeling. There is no commonly acceptable notion of model. I think we claimed here in this lecture pretty deeply that there is a commonly acceptable notion of a model. Modeling languages must be as expressible as only possible. My goodness, then we would have a universal language, whereas a universal word formula doesn't exist. See the Bible and other holy books. Modeling languages should be first syntactic and only secondly semantic. That is the claim made by computer science people that have been maybe very successful with using this kind of paradigm, but in reality, and natural languages especially, we don't have this kind of separation of concern in the syntactic and semantic matters. Yeah, we have a lot of hypes in computer science, and each hype must have its modeling language and forget about anything else what has been done before. Okay, the hype will vanish. Implementable modeling language should be minimalistic. That is also not true. It is better to have a proper approach to model suites. A model reflects main aspects of the applications and allows us to derive all other aspects. That would be nice, but it is impossible. See the discussion about the universal word formula. At its best, models are used for programming and coding. Okay, also a code can be a model, but maybe it is a model that is not readable by everybody. One model is sufficient for holistic representation. That is already a pretty difficult part. Modeling can be practiced as handicraft or maybe in its best as an art. That is also problematic because of models, and modeling should have at least a good and sound foundation. And for this reason we need to have a science of modeling. Maybe we will have later a culture of modeling. Modeling language should have a flexible semantics and fixed syntax, that is like UML communities are claiming. Okay, one special claim is all models are conceptual models. That is also a bit problematic. In his recent lecture, John Millard-Pullers made a claim that 3 theses are valid. Conceptual models are computational models of conceptual mental representations. A model must not be computational. A model must not be a model of a conceptual model. It can be something else. That means in this case we maybe are too strict with the model notion. Conceptual models are artifacts. That is maybe true for most subdisciplines in computer science. In general, it's also problematic. Conceptual models can be considered as social artifacts. Despite the matter that we might have models that are only representing our thoughts and are not at all artifacts, we should also look what it means. Computer science has been for a long time considering the computer as a primary issue, and for this reason the user was completely neglected. We didn't consider what kind of user interface we need. I think this turn is a very good one, but it is already valid since we have been developing websites that must somehow fit what the user wants to do. Okay, Scott Embler in the same paper declared 10 ways to ensure mistake-free design. Data models aren't sufficient foundations for modern software. That's true. We need a model suite. Embrace change and allow your models to evolve over time, and you can freeze them and hope to succeed. Okay, maybe. Models aren't necessarily documents, and documents aren't necessarily models. I claim that documentation and models are orthogonal features. Most models can and should be discarded. That is a problematic thing. In this case we have a model that was used for a green field for an initial development, and then we discard it. And then we don't know what has been somehow put into our software. Only the code is in sync with the code. Okay, fine. Why not? Simple tools such as whiteboards suffice for the vast majority of modeling efforts. That is a good starting point. Maybe at a later stage, especially when we are looking for realization of models, it is not sufficient. Think first, then code. That is a good claim. You can also always learn something from others. Yes, if the others are providing you this kind of experience and input. You can model in an agile manner. That is one of the things what we do in brainstorming. You can model also using other molds and other methodologies. Your design isn't finished until you shipped your code. That is a good claim for at least somehow resilient codes with having some kind of models underneath. Okay. Conceptual modeling is, of course, having a long history. In my understanding, at least 2000 years old. Conceptual modeling started in my community mainly as conceptual data modeling. Conceptual data modeling has been a very good success story, but it is not the only conceptual modeling. We have conceptual modeling in simulation, we have a lot of open issues that we should solve, we have a lot of research challenges, and of course we have some cohabitation of conceptual model solutions with technology advancement. So let me look for this one based on the paper that we have had with Jano Jakola in this year's EGC. First of all, we can sit back and be happy because we have a good success of conceptual modeling, at least in the database area. The linguistic foundation is, in my understanding, settled. We have a lot of modeling methodologies. They have reached a very good majority, at least at level 2 or 3. That means in this case we have at least a possibility to claim that conceptual modeling is somehow settled. We know how to handle distributed and federated database systems. Ontologies are another modeling language. They can also be used for harmonization of viewpoints for business users. Service architectures and provision have become a standard. And we have a lot of approaches that are pretty successful. For instance, question-answer forms combined with input-output forms. They provide a very good initial solution for maybe even a global communication problem. Database research and conceptual modeling data research is, of course, continuing. It is still an art and has not yet become a culture. We have a lot of different approaches, and each group uses their own approach. Integration and harmonization is still an open issue for research. Model transformation and active modeling has not become yet a standard, so we have some research topics we should really tackle. Co-evolution of database systems and models can be tackled by the models as programs approach. See chapter 14. Continuous modeling, independence on changes, is still a real big issue, is a major lacuna. Some issues have been closed. We will never achieve, and we now know that, the explicitity of natural languages. Pragmatics of modeling did not receive a common treatment. Research on object-oriented database systems is maybe one part, but not even the primary part of conceptual modeling. Interoperability is maybe considered as not feasible, and for this reason we should not really work on that. Knowledge and information management inside a database system is not really supported. That means we lost a number of topics that have been very, very nice in the past. We have, however, a good number of future challenges. We need foundations. Models should be used beyond description. We have no agreement so far in the community of practice. Maybe we should reach that very soon. We should overcome the logical separation of syntax and semantics. That is not really the nicest approach. We should concentrate on one abstraction level for data. We should use some kind of structure behavior separation. Maybe M0, M1, M2, M3 layering is not appropriate, but maybe it's appropriate. We need also to go away from the global as design approach. Maybe we should have some kind of generalized local as design approach that integrates local as design as well. We have also a number of good issues for research that are really pressing us to develop new approaches to conceptual modeling. Artificial intelligence and machine learning are somehow actual factors. There's a hype, but in reality there's also a challenge. Data science, that means modeling by somehow investigating data that we have, is still a very hard topic. Non-structured data, pipeline-driven data integration is still an open issue. Traditional database technologies will never disappear, but we will have a number of different technology mixed together. Database technology has reached the maturity to run in real time. That means in this case we can use it also for robotic process automation. We should maybe have a good number of specific problem area solutions. The complexity in modeling the large is still a research topic that will be tackled. Agile modeling, why not? We can do it faster, we can do it more, however, we should be aware of what are the benefits and what are the risks if we go with agile modeling. Just-in-time data modeling becomes very, let's say, interesting. We need a better automation and a better machine learning. We should also focus more on specific ways on data modeling. And of course, we should also know how we can handle migration, modernization of systems, or even radical changes. For this reason, a number of data conceptual modeling approaches should be reconsidered, revised, modernized. A flexible model transformation without information loss would be pretty nice. Large data models and weakly structured data are very important. Data models reflecting provenance and quality are also important. Adaptable and self-adapting data models will be really nice. We need also to handle migration, or let's say heritage extraction models. Just-in-time data models would be nice. Data models reflecting storage are separated from the data models supporting computation. Special data models for special tasks. We need also to cope with applications coming from other areas. That means we have to have or to handle lopment data models. Laymen are typically known specialists and are not educated in the style that we use in computer science and computer engineering. Of course, we need also to harmonize the data modeling approaches and the data modeling languages especially. Maybe we should also go the way how industry has been evolving, standardization of components and generic conceptual models. Okay, models in academia. Maybe we should found an academia of models, activities to model, and modeling as a community of practice. That means in this case we should have some kind of thought room, some kind of support for systematic model development and utilization, maybe some centers of competence. Maybe we can base it on a proper way how to extract a model, maybe based on interview techniques. And of course, maybe we should also support model-based reasoning. Let's start with the first one. A thought room for models, or a thinking room for models, that could gather modelers together to perform really research around particular MMM issues. MMM is models, activities to model, and modeling. The community of practice should be a group of experts that allows to use their experience by anybody else, by partners especially. We have already such thought rooms in the past. Think about agile brainstorming and origin forensics. We should maybe form an MMM community, processing the MMM knowledge and experience in such a way that everybody can use this experience, maintain maybe an MMM library, so that we have at least the full stories about the success cases. Maybe we should have some workshop and modeling studio. Maybe we should also discover and re-establish what has been done over the whole history of modeling. Maybe the history of modeling spans a period of 5,000 years, maybe more. For this reason, we should also look into the past experience. And of course, we should have finally a modeling theory, a modeling science, a modeling culture, and for this reason we will have a transdisciplinary model development forum. Are such thought rooms available or possible? Yes. And they are becoming more popular. For instance, we have now an initiative in Kiel on a thought room for general issues for development in sciences. We could have the same as a thought room for modeling. In this case, such a center of MMM competence would of course include MMM as a library, MMM as processed knowledge, MMM as a society for joined up thinking and transfer. And we should also in this case provide MMM as a service for everybody, especially for our contributors and partners. That would be a thought room we could somehow realize in the future by combining all results we have got in the past. In order to have such, we should have a systematic approach how to develop a model. I have been using in the past this kind of mind map techniques to specify what are the models that are used in different disciplines. This model interview is based on interview techniques widely used in social sciences and somehow combines whatever we have been knowing about models. Now I present here a little bit more modern viewpoint. You go of course first with the utilization scenario and use spectra. You have to specify what is the community of practice that is really interested in having this model. What are the artifacts and the origins? What are the sorts especially also? What kind of portfolio and profile the model has? The instrument is used as a model, so for this reason we have to specify what it means. That means in this case we have also somehow kind of notion for dependability, for adequacy, maybe for other resulting properties. And of course we should consider also the context. And finally we can think about how this model can be used efficiently and effective, at least in the scenarios that the model should function as an instrument. We can use this kind of specification framework, for instance, also for extracting the deep model parts or the matrix especially. I provide here an insight into the matrix for models in archaeology. Of course, we have to have a basis, we have to have a grounding, and in this case we should say what are the concepts that we are using in the basis, what are the accepted hypotheses, what are the theories we are using, what are maybe the thought approaches and the thought schools and biases we have to handle somehow. Of course, a model has a profile. The model profile can somehow be used to especially specify the adequacy and dependability, as we have been doing in the last lecture. And of course we have to consider the context and the scenario in which the model is used, what kind of investigation we have to have. The basis is of course based on a number of, let's say, concepts like what is, for instance, a village, what kind of centers we are considering, what kind of social structures, what kind of general relations and architecture we are considering. We have a number of other concepts, and of course we have a number of, let's say, hypotheses. This would be some kind of a specification frame in our model interview. Okay, then we can specify that a certain object, maybe also a certain sort, but let's do it first for an object, for a material object, is considered to be a model. What we shall do is, of course, we shall give some kind of description of the object. An object has typically a number of associations to other objects, especially the origin relationship, or maybe other relationships. And the object has been or will be used in a certain number of scenarios. If we know this scenario, then we can say, okay, fine, this object has a good utility for people in our community of practice, either consumers or maybe deliverers. And then we can say, okay, fine, then in this case we know what is the function in a given scenario of that object. Based on that, we can now specify the adequacy and dependability. We can also judge why this object is considered to be a model. Of course, it will be given by somebody who judges. Of course, it will be also stating that this judgment has to have some kind of description why we consider this object as a model. In this case, it would be nice to use some kind of stereotypical development. That means in this case we should use maybe model categories. Model categories allow us to say, okay, fine, this kind of object is now a model in a given model category that we have been already generalizing by a number of models, so that we can say, okay, fine, it is, for instance, only a representation model, or it is maybe a prescriptive model, or maybe it is even a reasoning tool. Then in this case, we can now specify that, of course, this specification we have here belongs to models of that model category, and the material object is considered to be a model. And then we can summarize the whole thing. This approach would be also nice because in this case we can derive a number of informations from the model being of objects. We can compare this model with other models, we can compare other objects that might not be of the same kind, of the same category of model, but somehow are associated. That means in this case we know at least what kind of association we have to use. Okay, and in this case we can now also apply our model-based reasoning. As already shown, we have some kind of hypothetical reasoning, some reasoning approaches, especially those that have been developed in logics. We have, of course, a number of stories to consider for this reasoning, and then we have to have maybe specific approaches that have been developed especially for models. For instance, for some kind of abductive or inductive models. And in this case we apply inductive reasoning approaches. For instance, let's say this Solomonoff reasoning that is based on a number of principles of inductive reasoning and of efficiency and effect of our models. Okay, that means in this case we could have a model academia. The model definition we gave so far is a pretty general one. And in this case, maybe we should have a path to specialize for specific frames, for specific, let's say, landscapes, matrices, for specific dependability, and for also specific categories of models. Okay, we can use the frame that we have been already discussing. We have a certain application scenario, and something should have a role, a function in that scenario that will be called model. So in this case, our application space has also a task space with a number of objectives, goals, actions, a number of preconditions, and we have also something like this Ishikawa diagram for the causes and the necessities for the problems we have been observing so far. And what we would like to have is a result of the model application. That means we have, in this case for the function, a delivery space for the information, descriptions, actions, actors, capacity and potential. And in this case we can say, okay, fine, a model is now, or something is now an instrument, and a model in a certain category and with a certain specifics. It is somehow reflecting origins, which have again a cargo, but the cargo is also inherited by the instrument, so that the instrument carries the cargo as well, and it can be used for deriving, for computing, for developing a number of results we are interested in. That means in this case we have also an environment enabling modeling, and we have also tools in support for modeling. That was a general picture. We can use it also for a very specific picture. Think about what we have been already discussing about the problem. We would like to know what are, let's say, the problems we can observe for human heart insufficiency. So in this case we have of course to have a behavior space. In this case we are using as origins hard models, for instance as a volume pressure model. So in this case we would like to have some kind of hypothesis development, and in this case our model should be used or should function for dependence detection. In this case we can say, okay fine, we have now what we will use for the result of our modeling or model utilization, some kind of behavior traces. We would like to see what are the main influencers for certain problems we have in human heart, or for improvement, what kind of control parameter we should have, maybe using some kind of synergetics approaches, what kind of methods we can use for influencing the problems of human heart insufficiency. So in this case we say, okay fine, we would like to have some kind of investigative and explanation model as a stereotype. We use already existing models like human heart models or volume pressure models, the heart is a pump, and we say, okay fine, in this case we can use maybe a completely different way, and this was already done by Danbokov and others. We use an electrical circuit model that mimics the behavior of the volume pressure models, and we can show now what kind of behavior we have, and using this model we can somehow know what kind of, let's say, proposals for chemical treatment or for pharmaceutical treatment we can have, what kind of problems we have with the most influential parameters. So in this case we have again our model that is from a completely different area for representing the origins and for deriving or having a good result, and for this reason we can reason about the problems we have maybe with human heart. So in this case I would call this model approach some kind of a playground model. So it is used as an instrument for human heart investigation, at least for the problems of human heart insufficiency. That means in this case you can say, okay, then we have a number of facets of models. We claimed already that we can stereotype the model specification. We have a kind of model, we have origins, we have a landscape, we have a community of practice, we have the adequacy and dependability. The dependability especially can also come from our frame that we are using, That means in this case we can use some kind of instrument frame and some kind of quality and evaluation frames we can use here. And additionally we have maybe some additional dependability properties we can add for the instrument. We have a basis coming again from the instrument and from the deep model we have been integrating into the instrument. We have a grounding coming typically with a deep model. We have a context coming with a matrix. And then we can say, okay, fine, a conceptual data model is of course maybe consisting of more than one model and reflects a good number of origins, so that we have some kind of application domain model, we have some kind of realization model, and then we are represented by a conceptual database model. The modeler is interested in that, and the implementer as well, especially if we have prescriptive or prescription models. We have in this case a pretty nice adequacy that is some kind of homomorphical or infomorphical treatment, and the infomorphism maybe is the most reliable notion for having some kind of generalized mapping. We would like to have some kind of similarity. We are basing our thoughts on computer science and information systems paradigms, and for this reason we have to consider those in our deep model and also partially in our instrument. In this case we go now, let's say, for the relational database management systems. We have data and we have maybe some specific branches of applications to consider. It would be completely different if we go for a completely different kind of model, for instance for metaphorical models. They represent some kind of observations on reality. They provide an annotation. We have a speaker-hero approach. It should be somehow transferable. It should be pretty simple, so that we can really have some kind of parsimony. We use in this case maybe the lexical semantic from our languages. We have some mental properties, and of course we somehow realize it in our current way of thinking. Biological function models are of a completely different kind, as well as mathematical evolution models, or let's say information system database mediator models between the application and the code realization. That means in this case we can say, okay, fine, having this kind of specialization, then we can say we need this kind of model for these specific applications, for these specific functions the model should have in these scenarios in the applications. We can use now this for a classification of models. I would like to show it with a classification that is pretty well known, at least it goes back to Ortlieb, for the classification of mathematical models. These are essentially specialization facets. We can separate or somehow distinguish models in mathematics by their transparency, or by according to the applied mathematics. We have here black box models, white box models, gray box models. We have, according to the mathematics, maybe static or dynamic models. We have deterministic models or maybe stochastic. We have maybe discrete models or continuous ones. We are considering the microscopic level of detail. We maybe use some kind of exact models with maybe some errors we are using there. We can also separate the models and classify the models by problem areas. We have planning problems, we have explanation, and some kind of relationships, at least at the phenomenological level. We have a separation into good and bad solutions, let's say for optimization problems. We have interaction models. And we can also go by the degree of details. It means in this case we can use this kind of classification of mathematical models for directly using some kind of specialization, and then we can say, okay, fine, we are only talking about macroscopic optimization, white box models that are somehow even exact and are used for reasoning about demography. So, modeling is, in my understanding, a separate disciplinary subdiscipline in computer science. I can claim further that modeling is the fourth dimension, or the dimension number 4 of computer science. Models don't have to be theories, they don't have to reflect only situations, so they are somewhere in between. Let's consider this. First of all, my claim about the fourth dimension of computer science. So far in computer science we have been widely using states in the large or in the small, let's say in the small like in the database schemata, or in the large as we are using in software engineering for architecture. We have also transformation, and since we are mainly oriented on state-oriented approaches, we have a transformation applied to states. We can also have an event transformation. Of course, in this case we have again the whole transformation in the small and in the large, as evolution of changes, maybe, or as the changes of states, maybe by rules or by computations. So in this case we have at least the two classical aspects. Another aspect came into when the computers have been really applied in practice. So in this case we should consider collaboration. Collaboration can be best specified on the 3C paradigm, specifying communication, specifying cooperation, and specifying the coordination among states, among transformations, among systems, or of systems with users. And of course in this case we are using some kind of exchange architectures and services. Think about the Lopment approach in this case. And the fourth dimension is based on abstraction and mapping on some kind of construction. It is also based on some kind of idealization, distortion, extension, and amplification. Oh my goodness. So in this case that means that we have as a fourth dimension modeling. Okay, quite often we have the question whether models lie in between situational representation or theories, as a mediator between the state of affairs and theories. That is a problem. We have, of course, models that are reflecting pretty nicely what has been observed, what kind of situation we have, what kind of state of affairs we have. We have also models that are somehow representing the theories. But in this case, the model is somewhere in between, as between the line of between situation and theories. I claim, however, in reality, models are an orthogonal element of sciences and especially also of computer science. We have a situation, we have a state of affairs, we have theories, and the models can be used for representing the situation. The models are illustrated by a certain prototypical situations at least. The models can also use for comprehension of a theory, or we can understand the model by a theory. The relationship between situation and theories is of course based on a number of scenarios. I was putting here only two: exploration or explanation. So in this case we have now models as an orthogonal element of computer science and also of sciences. Another observation we can make. Jim Gray has been introducing some kind of fourth generation of computer science, of science in general. I will transfer it or explain it with a little bit different revision. We have here empirical sciences, theory-driven sciences, computation sciences, and data exploring sciences. I was already using this kind of ladder. Among the sciences, of course, you never have a science or a discipline that is only tackling one of them. Typically, you have maybe all four or three or two of them together. In this case, we are using models, but we are using models a little bit different. In empirical sciences, we can use, for instance, models for visualization of phenomena, for experimenting, for observations, for explanation of the current point of view. That means in this case we have some kind of scenarios: investigation, making a statement, communication, discussion, negotiation, coming to a common agreement. That means in this case we have a number of approaches. So the model is in this case mainly used as a very nice tool for empirical sciences. In theory-driven sciences, we go back to this kind of separation of concern into situations and theories. Then in this case, we have, of course, models for representation, for learning, explanation, for communication, understanding, and we have a number of scenarios we are still using. With the advent of computational sciences, we can use other models for mediating or starting points, let's say for inverse modeling. Then in this case, we would like to investigate behavior, predict, forecast something, what is done quite heavily with all that numerical approaches, numerical analysis in mathematics. And recently, that was a claim made by Jim Gray, we have a data exploring science. Then models are using as a starting or a mediating point for hypothesis and investigation and pattern detection and summarizing. Okay, let me come now to the final remarks of these lectures. What has been left? What has already been investigated? Okay, what we have already pretty ready is we can integrate top-down and bottom-up processes of model development, and models are unfolding dynamically. We have already a number of modeling styles that can be combined to modeling cultures. We can think about models 2.0. We can have maybe a selection of principles that is even adjustable depending on the model function, of course. We have a number of explicit treatment of model value, and we have coexistence of theories, languages and tools. And we have, of course, a number of switches and maybe more case. We have a number of research issues. Model suites, model evolution and revision is still a big issue. Of how we handle variants of models for different usages in a coherent, consistent way, based on maybe a very good mathematics, like we do, for instance, in entity relationship modeling. We use diagrams that have maybe a canonical semantics that can be used for canonical representation. At the same time, they can be used also for a very formal treatment, and of course also for derivation of the implementation structures, as we have been already considering in this lecture. Maybe we should have a good way how to form the MMM community, the MMM academia. Then in this case we need to have some kind of experience that can be transformed. We can consider specific kinds of models, specific stereotypes. We should also be able to control models, activities to models and modeling, and should be able to handle complexity. I dream about compilers for models as programs. In this case, we might have an automatic programming by models. The science of MMM is on its way, but it will be a common effort within the entire computer science community. And of course, we should also have some kind of specialization adaptation for specific disciplines or subdisciplines. It seems to be that all is novel, that all this is novel. No, it is not really true. There is a word, logos, in Greek language. It goes back to the introduction by Heraclit. The logos has a number of meanings. It is a word field with a number of meanings. Of course, it is a word. It is a mind. It is maybe the power and the application, the deed, how it was done in Goethe's Faust. It has three more variants. It is a concept, it is a judgment, and it is a tool for reasoning. So in this case we have word, concept, judgment, mind and meaning, power deed and act, and reason. In German language we have Wort, Begriff, Urteil, Sinn, Kraft, Tat, Vernunft. I was using here the German column as well because of we have some false friends. We have concept in English, that is in German Begriff. And the Begriff is the concept. A concept in German language is nothing else as a draft, a rough or first draft. It can be also used as a conception, or Konzeption, that means as a plan. And the conception, however, is again something else. It is the Vorstellung. That means in this case we should know that the word fields for words in German language and in English language don't match. In this case the word is nothing else as syntax. Concept is conceptualization. Judgment is of course accepting something. Mind and mind making, meaning making or sense making is nothing else as semantics. Power is usability. Deed and act is application. And of course reasoning is rationality. That means in this case we have well-formed instruments with a background, we have conceptual models or conceptual instruments first, we have adequate instruments, and if we have adequate and dependable instruments we can have a model as such. Then we can have maybe an appropriate model, we can have an effective model, and we can have a well understood model. So that means in this case, in order to consider the science of modeling and moving towards a culture of modeling, we should also use whatever has been done in the past. As a little comment on all these lectures we have been giving. Sometimes it is also claimed that middle range theories, especially in social sciences, are a bit different from modeling. A middle range theory is nothing else as a theory with a limited scope that explains a specific set of phenomena, as opposed to the grand theory. In archaeology, it is used as a link between the qualitative data and concepts and the quantitative data and concepts. That means in this case we are using some kind of quantitative data in order to have some kind of interpretation by concepts, and in this case we come to equality. What we observe, however, here is that there is nothing else as using models. Models for explanation, for investigation, for exploration, for problem solution, for construction of solutions in systems. That means in this case a middle range theory is nothing else as a bundle of models, a model suite that is used in different ways. So this is now my final remark. Furthermore, at the end of this lecture series, I would like to thank my Christian Albrechts University modeling community. As you can see here, my colleagues were coming from very different scientific and engineering disciplines. They have been contributing a lot for a little bit more than 10 years even to investigate. I was putting here in boldface Ivar Nissen because of with him we have had together this compendium about the modeling approach we use in this community. So I would like to thank my community. You see here the analysis result of these communities, unfortunately in German language, but I think this was the only way to agree on a common approach for definition, usage and future of modeling. My background is of course a database background, conceptual modeling, using some specific language and applying it for the development of web information systems. For this reason I should also thank my collaborators. That is now a pretty large list, and I think it is not a complete list of all my collaborators over the time, where I was putting mainly only those where we have common publications. And of course I should also thank my background. These are the people who have been somehow pushing me to the right track over the last 45 years in research. You see here also names like Andrei Nikolaevich Kolmogorov or Boris Trachtenbrot, but you see also names like my colleague from Robotron, Jürgen Bittner. All those have been guilty to forming my thought. Maybe at the end we should make some fun. You can have a lot of funny notions of the model. One is, for instance, you can say, okay, fine, an artifact is a model because our leader told us. Or you say maybe an artifact is a model because it is evident and thus plausible. Or you can say, no, a construction is a model if it reflects reality and is digestible. Or you can use our authority notion. An artifact is a model because of accepting authorities. Or you can say, no, a model has to be convincing, and for this reason the artifact is a model if it is convincing everybody. Or you can have maybe a model is simply good and valid, for this reason we can use it. That is maybe some fun at the end of this lecture. So I would like to conclude now with the lecturers thanking you for participating, for listening to the lecturers, hoping for your critics, remarks, proposals for future development. That means in this case we took now a long journey. Now we have to relax, take a shower, and then apply everywhere, and after that we can somehow relax and digest all. Thanks a lot for this lecture.